Hey guys, welcome. Yeah, so by the end of this video, we're going to figure out what we mean by a group in mathematics. And this is the first of a number of videos on groups and the first of many videos on abstract algebra. Abstract algebra was my favorite subject in college because it showed me how flexible math can be. Yes, past calculus analysis was also satisfying and getting away from computation and showing you how to think more generally about mathematical ideas. But it was abstract algebra that for the first time showed me, hey, there are some philosophical consequences to math, and it's a lot more malleable than I thought. And of course, beyond that, I really enjoyed complex analysis, and topology is even more mind bending, right? But I'm not saying that abstract algebra is the only place where you see math being very flexible, but it was the first time I encountered that notion. Okay, anyway, a group is something that you study at the start of abstract algebra. And the reason why you begin with groups is because groups are the most basic structure that we can put on a potential number system. Yeah? Okay, alright. Now, there are structurally lighter things like monoids, which is the requirement to be a monoid is even lighter than the requirement to be a group. But what a group is, a set that has some elements. So a set together with a binary operation star, and we're calling the binary operation star to make it more abstract because star can be addition, it could be multiplication, or it could be something else. Just to show the flexibility of this group definition, my second video on groups is going to teach you how to add fruits. So how to add oranges and bananas, and there we define the binary operation to be juicer. So this is what I mean, it's kind of abstract, but yeah, it's just, and notice that in that example, banana and orange are elements of your set. So what you have is a set with some elements, and then the set together with a binary operation star, such that the set has, these are the requirements, the set has a neutral element, so something that acts like 0 does in addition. So when the binary operation is addition, then 0 is the neutral element, because when you combine any element with 0 with addition, you're going to get that element back, right? And so and the traditional definition of addition, right? So that's what we mean by a neutral element, something that acts like 0. Okay, and then an inverse element for every element in the set. So here I've said the yin yang because it is exactly like that. So your inverse element is that which when combined to you with the specified binary operation takes you to the neutral element. So for example, if we're talking about binary operation addition and our set is the integers, then the inverse of 5 is -5 because, well, when 5 is added to -5, we get 0, and 0 has the special property of being the neutral element. And if we're talking about say rational numbers and then multiplication, then 5 has as its inverse 1 over 5, because 5 times 1 over 5 is equal to 1, and 1 is special because it's the neutral element with respect to multiplication. Yeah? Okay, so a yin and a yang. So every element has something that when combined with the binary operation takes it to the neutral element. Okay, so 2 here, and then closure is also required. Closure with respect to the specified binary operation. And what closure means is that any two elements in this set, when combined with the binary operation, become something new which is also in this set. So if your set is 1, 2, and 0, then if you combine any of them with another, then it has to come back to 1, 2, or 0, right? Okay, and that was an odd way to say 1, 2, or 0. 0, 1, 2 would have made more sense, but it's fine, it's fine. I'm going to show you an example, so in the context of the example, we will see exactly what we mean by closure if you don't get it. But basically, combining two elements with the binary operation gives an element that is in the set also. That's what closure means. Okay, and then the final requirement is associativity. I know how to say that, guys. This is like literally the first time I've messed up saying associativity. We also need the associative property with respect to the binary operation star. And so, that means that parenthesis A star B, and then outside the parenthesis star C has to be equal to A star parenthesis B star C, and that has to be true for any A, B, C in the set, and that's what we mean by associativity, right? Okay. Now let's look at our specific example. So let's take the set 0 and 1 together with the binary operation addition. Then we can form the group table this. And it's not called a group table, it's called a Cayley table. And so a Cayley table is a good way to demonstrate that a particular group is well defined, because we'll see, like we know now, that 0 plus 0 is 0, and so on. And so we can quickly check if we have closure, which is, like any combination here, whether we do 1 plus 0 or we do 0 plus 1, the result is displayed here, right, in the Cayley table, and so we can check that it is in fact closed, right? This set with the binary operation addition is closed, right? And notice also we've defined 1 plus 1 to be 0, which is a strange thing to do, but we're allowed that, right? Like, because this is a looser requirement than the requirement placed on the number system that we use, which would say that 1 plus 1 is equal to 2, right? Okay, anyway, this group is well defined because it's closed, and then every element has an inverse. So the inverse of 0 is 0, and the inverse of 1 is 1 itself, because 1 plus 1 is equal to 0, and 0 plus 0 is equal to 0. And it's pretty easy to see from this table, from this Cayley table, that 0 is the neutral element, the identity element. So we've kept that still true, even in the context of this set with this binary operation and this table that defines what happens with the binary operation. Now, the last thing that we need to do is check associativity, right? And so for that, we can check this, and we see that this is what we're going to get, right? Like if we check if 1 plus 0 and then plus 1 is equal to, then this is checking for associativity. We see that 1 plus 0 from the table is equal to 1, so we can replace this with 1, and so we get 1 plus 1 on the left side of the equal sign, right? And 1 plus 1 is 0, right? We can see that from the table. And then on the right hand side we see 0 plus 1, so 0 plus 1 is 1, and so we do that, and 1 plus 1 again is 0, so it's good. And clearly this is not exhaustive, this is just me demonstrating, but you can check this table and it will pass associativity regardless of how you choose your elements. And just for like an extra check, to make you feel more secure, here it is. And the next video, where, as I said, we will add fruits or add with fruits, I will show the associativity property exhaustively. Yeah? Okay, cool. Otherwise, I hope you've enjoyed this, and look out for more videos on groups, and take care.